Okay, everyone ready? So let's go back to our Fourier transform properties. So as we said, these properties are very similar to what we have in Fourier series. And let's just have a review again for this conjugation and the conjugate symmetry property. So first is conjugate symmetry, and we say we took a start. We put a complex conjugation on our time domain signal. Then we need to do complex conjugation and also this frequency reversal on our frequency domain signal. Okay, this is just like in the AK case where you have x over t got a star, then your AK got a star minus k. And so similarly, you have that if we are real, then then we have that x of minus j omega equal to x star of j omega. This is similar to this a of minus k equal to a star of k in the periodic case. Okay. And then we have an example of this happening. That is, we have this real signal, example 4.1. Our signal is this one-sided exponential decay, so e to the minus at u of t. And okay, so this pair is very important. We'll use it all the time, so let's see it more times. Okay, so x of t equal to e to the minus at u of t. Then big X of j omega will equal to 1 over a plus j omega. And a need to have a positive real part, so this will converge. Okay, and then we see that this is a real signal, so this equation should satisfy. And indeed, you can check here. So big X of minus j omega, well, you put a minus sign on omega, and you have a minus sign on this, so it's 1 over a minus j omega. And the same as you put a complex conjugation on this thing, because complex conjugation, then you put a minus sign on j, and you have 1 over a minus j omega. Okay, so you see that this property check out on this signal. And then we have a more complicated thing going on. Okay. And so there are two things. So first is, so now we have a lot of more analysis on what happens when x is real. So if x is real, and we know this thing, and then we can do two things. So we can decompose our big X in terms of rectangular form, so to a real part plus j and the imaginary part. And then you think about, then you basically take the frequency reversal on both and take complex conjugation on both. Then you see that complex conjugation don't change the real part, so the real part is just equal to its frequency reversal, so it's an even function. And if you do complex conjugation on here, then this j give you a minus sign, and so the imaginary part is negative of the imaginary part with frequency reversal, so imaginary part is the odd function. Okay. And similarly, you can do similar thing on the polar form. So you have the magnitude part and the angle part. Then you see the magnitude. So if you do this carefully, you see the magnitude part is an even function, and the phase part, so angle part or the phase part is an odd function. Okay. And then then we go back to adding more things. So you can go back to adding when x of t is even function or odd function, and so we skip the derivation here, but because it is similar to the periodic case. So periodic case, we have that if x of t is even, then big X of j omega is even, and also x of t is odd, and big X of j omega is odd. I guess going a little bit. So in the periodic case, we have that x of t is even, then the ak is even, and the x of t is odd, then ak is odd. That's because if you do time reversal on x of t, so we have that. That's because we had that x of minus t will go to a of minus k, and here is a similar reason. Okay. We have that you have x of minus t, then we have a big X of minus j omega. Okay. So here we also have x of minus t is Fourier transform pair is big X of minus j omega. That means the even odd property. This will give you that the even odd property of small x will be sent as the even odd property of big X. Okay. And then, just like in periodic case, we can string together even odd analysis with the real imaginary analysis. then we see that if you are real and even, then big X is real and even, and if you are real and odd, and the big X will be imaginary and odd. I guess those you can do derivation, but so we have a table here. But the more important thing to remember is probably the first four. Okay. So let's remember is the first four. Okay. So the first two are, I think they are easy to remember. You just remember the X of t even odd, same as big X of even odd. Then you need to remember this. Then, and I guess the first three is most important. Okay. Because those first three are the ones you use most often. So that's erase and highlight them. Okay, so the first three. So small x even, then big X even, small x odd, big X odd. And if small x is real, then big X has this its complex conjugation equal to its frequency reversal. Okay, and then this is sometimes you might see this, that if small x is imaginary, then your big X has this property. But the first three are the ones that you will see most often, because physical signal can have those three. Because like physical signal, usually it has signal is real, and sometimes you have some symmetry, then your signal can be even or odd. Okay. And yeah, so you combine those four, then you can get those four just 2 by 2. Okay. Okay, that was a small review of this property from this time. So everyone understand? Okay. It's okay, then let's do this thing that we also do in chapter 3. Okay. And this is a decomposition of the real function into the even and odd part. Okay. So we start with our real function, so kind of this property. So we stay real, and so it's real, but this x of t is not particularly even or odd, but we can make an even and odd part out of it. Okay, so x of t is already real, and we make it into even part and odd part. And what happened is, is already real, so both of them are real. Then obviously this one will be real and even, and then this one will be real and odd. Okay, and okay, and so when we do Fourier transform on those three things together, okay, so this is similar to what we do in chapter 3, but actually a little easier, a little simpler. I was being a little, I was digressing a little bit when I do this derivation in chapter 3. But anyway, so x of t is real, then you can pick into the even part and odd part. And the even part will be real and even, and odd part will be real and odd. And when you do Fourier transform on x of t, by linearity, the Fourier transform of this will equal to Fourier transform of the even part and plus the Fourier transform of the odd part. But as we say, this is real and even, so this is also real and even. Okay, yeah. So this is this Fourier transform thing is also real and even. And this Fourier transform thing, and we can go back to the table. Okay. So if x is real and odd, then x of j omega is imaginary and odd. Okay, imaginary and odd, imaginary and odd. Okay, and then we kind of forgot about even and odd. Okay, so even and odd is cool, but then the thing we try to notice here is this part is real and this part is imaginary. Okay, and okay, so we see that the even part corresponding to a real function, and the odd part corresponds to an imaginary function. And we know okay, so this is f of, so we see the Fourier transform of x of t equal to some real thing plus some imaginary thing. So this is a real plus imaginary decomposition, but we know the real and the imaginary decomposition is unique. So this just corresponds to the real part of f of xt, and this just corresponds to the imaginary part of f of xt. Okay. Okay, so maybe let me draw a little more arrow. So because this is real and odd, then this will give you this, and because because this is real and even, because this is real and even, this is real and odd, so it will give you those. And because it is real and even, it will give you those. Okay. Okay. And yeah. So we see that. So by the analysis we just did, we see that the even part of x of t, you do Fourier transform and they give you the real part of big X of j omega. And the odd part of x of t, you do Fourier transform, you give you j times the imaginary part of x of j omega. Okay. And yeah, so this is a nice property, although you can just do derivation from things. And this is a nice property to know, and we'll see example how this will give you. Sometimes it gives you easier calculation of Fourier transform. Anyway, so this is what we try to memorize a little bit. So if x of t is real, this is the, the prerequisite that you need to remember. So this whole analysis starts from x of t is real. So x of t is real, then you put it into even part and odd part. The even part will be real and even, odd part will be real and odd. And when you do Fourier transform, then this real and even part go to real and even part, and the real and the odd part go to imaginary and odd part. So you know this even part go to real and the odd part go to imaginary. Okay. Okay. And so how do we use this to do calculate Fourier transform is okay. So we actually have two functions here. So we use it to calculate the Fourier transform of this function. X of t equal to e to the minus a absolute value of t. So this is x of t. Okay. So x of t look like this is exponential decay on both sides. So this is t, and so because you have absolute value here, and a is a positive number, so it's absolute value, and so it's decaying to exponentially decaying to positive time, and also it's exponentially decaying to negative time. And this was in example 4.2, and we skip this example, but it has some answer. And so we try to find the big X of j omega corresponding to this. But so you can do direct integration to get the big X corresponding to this small x of t. But what we are doing is we try to use this even odd property to derive this. And so what we use is we know our favorite example 4.1. So maybe I'll draw here. 4.1 we have this signal. Okay, x of t equal to e minus at. Okay, this is let's call this x bar of t to distinguish from this x of t. Okay, x bar of t look like this one-sided exponential decay, and it's all zero here. Okay. So we know this x bar of t is equal to e minus at u of t, and we know it's Fourier transform because we just memorize it. Okay. So x bar, big X bar of j omega equal to 1 over a plus j omega. Okay. And so how we relate x bar and the x of t is doing the even and odd part. So we see that x of t look like really like x bar of t, but if you just copy paste this thing, if you just flip this exponential decay to this side and add them together, then it looks really like x of t. And yeah, so that's what we did. We see that x of t equal to e minus at, e minus a absolute value of t, and it has this positive part and a negative part. And so the positive part look like so it's a positive part plus negative part. So the positive part look like just this exponential decay. Sorry, the positive part look like just this exponential decay, and the negative part look like this exponential decay with minus t. Okay, and so really your x of t. Okay, so this is the time reversal of our x bar of t. Okay, so x of t look like x bar of t plus the time reversal of x bar of t. So maybe I'll also draw here. So the time reversal of x bar of t, x bar of minus t, will look like this. Okay. Okay. And so if we add the x bar of t and the x bar of minus t, sorry, the minus t here, the minus sign is not written well. X bar of minus t. Okay, so we have x bar of t and x bar of minus t, and if add them together, they looks like x of t. And also we have the x bar of t plus x bar of minus t divided by 2, then that's actually the even part of x bar of t, because that's the definition. You add a signal and it's time reversal, and together divide by 2, then this is the then that is the even part of your x bar of t. And so you divide by 2, then you multiply 2 together. Okay, so you see that x of t is actually twice the even part of x bar of t. Okay, and then now is a small quiz. No, so now we see that x of t is the even part of x bar of t, and now we need to memorize. So we say x of t is it's actually both bar here. Okay, but I guess it doesn't matter. Okay, x bar and x bar. Okay, so now the quiz, small quiz. So now we have the x of t correspond to the even part of x bar of t. Then the big X of j omega should correspond to which part of x bar of j omega? It's either real part or imaginary part. That's what we did just a few minutes ago. So I guess if you think it's a real part, raise your hand. Okay. And if you think it's an imaginary part, raise your hand. Okay. I guess at least the ratio is good. Okay, so that's the real part. Yeah, that's correspond to the real part. Okay, so we say our function is the even part of this x bar of t. Okay, so yeah, because our x bar of t is real, and we have the symmetry property, and it says that the even part of x bar of t go to the real part of big X of j omega. Okay. So yeah, and back to the beginning, we know this big x bar of j omega is 1 over a plus j omega, and yeah, so we take the real part of this. And so our x of j omega is, now remember this 2 here, twice the real part of this 1 over j omega, a plus j omega. And yeah, and you can do some complex number calculation and see that the real part of 1 over a plus j omega is 2a over a squared plus, is a over a squared plus omega squared. And if you do the direct integration calculation, then you will see that this is the same answer. Okay. So yeah, so that's a little trick you can use by this real and even odd analysis to get some Fourier transform. Okay, question. 所以我们有2个function，所以有 x of t 是一个长这样的function，它是 e to the minus a absolute value t， 它是两边都 exponential decay 的。然后 x bar 是这个一边 decay 的 exponential function。那我们说我们知道 x bar 的 Fourier transform， 因为我们已经看过它。那我们要从 x bar 的 Fourier transform 去算出 x 的 Fourier transform。对 ，yeah。所以感觉大概是我们有x of t， 然后有个x big X of j omega， 然后有个x bar of t， 然后有个 x bar of j omega， 然后这个是，然后 x of t 是它的 even part， 那我们就知道 x big X 大概是它的 real part， 这种感觉。有问题吗？ Okay, understand? Okay, if you are good, then let's go to next property. Okay, next property is actually more interesting because we didn't have quite the same thing on chapter 3. Although, okay, so we did have its differentiation property in chapter 3, and this is similar, but I guess let's do a derivation because it's really quick. So first is the differentiation property, and it's kind of similar in chapter 3. So we say we have x of t and its Fourier transform paired to some big X of j omega. Then we take dx dt, and we want to see what the dx dt Fourier transform to. Then we just take ddt on both sides. Then this side becomes dx dt, and ddt on this side. You see only c dependent on t is this e to the j omega t. So you just get extra j omega here. Okay, and yeah, so you see that this is like this formula, but instead of big X of j omega, you have j omega big X of j omega. So you just think this j omega big X of j omega is the new Fourier transform, and indeed that's what happened. Okay, so yeah, so you take a differentiation on the time domain, and you get extra j omega here. That's very nice, and this will also be a little digression. This will be useful in solving differential equation, because when in differential equation you have a whole bunch of derivatives on your equation, and yeah, and so this is how you deal with a lot of derivatives. You do Fourier transform, and they just become multiplication of a whole bunch of j omega. Okay, and but let's go back to our property. So this is differentiation, and it's similar to the periodic case. Okay, but in integration is really weird. And okay, in the integration, in the periodic case, we just say the integration doesn't work because the periodic signal basically cannot do integration to get a final answer. But now we are aperiodic, we can actually do integration, and then we have this signal, and we say it's integration from -infinity to t, and x of tau d tau, and so this is some function of t, this is t here, and we will think that integration now should be the reversal of differentiation. So you have j omega here, you should have 1 over j omega, but I guess we just stay without proof here. You will also have this really weird term here. Okay, so you will have a very divergent term of pi big X over 0 delta omega here. Okay, so yeah, so here's a reminder. So you have dx dt, you have j omega big X over j omega, but you try to reverse this thing by doing integration back. Then you see that in addition to this 1 over j omega, canceling your j omega, you also get this pi x over 0 delta omega term. And it's hard to explain this term. Basically, the idea of this term is you do integration, then you will get some DC or average term. And I think it's easier if you see an example to see what we mean by DC or average term, average value term. So what we mean by this DC term is like this. Okay, so let's say our x of t is So we have the integrated function and the original function. Okay, so it's a little confusing. Anyway, the notation is here. So is this? So we have a g of t. So we have this function. That's just delta function here. Okay, and it's a delta function p get 0. Okay, and we know its Fourier transform is 1. Okay. And so let's think about what we do integration on this delta function. Okay, and we know the integration of delta function is this unit step function. Okay, so you keep integrating this thing, then it's all 0, and then you integrate through this delta function peak, then you get 1. Okay, so yeah, so you start with the delta function and you do integration, then you get this unit step function. Okay. Yeah, so we have a g of t and the integration of g of t, which we call x of t. It's a little confusing, but yeah. So g of t and the integration, then you get x of t. So far, so good. Yeah, this is chapter 1 thing. And so what do we mean by DC term? What do we mean by DC term is basically this unit step function thing. So see, you have this unit step function, and it's really not really oscillating, but you have but it starts with 0, and it just at some point become this constant throughout, throughout all the time to infinity. And yeah, so this step is the change of height, I guess. This step thing is kind of what we mean by DC term. So as I try to say a little more, so we think our g of t is something localized in time. So if our g of t is something localized in time, right? So now periodic and something localized, then you think your integration will also be localized. So it should be kind of flat at -infinity and kind of flat in +infinity. But what we mean by DC term is that the flatness of minus infinity and the flatness of plus infinity might be different. Okay, so as you see that you can have a unit step here. So it's flat at plus infinity but at height 1, and flat at minus infinity but at height 0. Okay, and the change of height is what we mean by this DC or average value. Okay, and the change of height will give you a delta function. And so we just plug in a formula to see what we get on this delta function here. Okay. So our x of t is now this integration of g of tau d tau. And we just plug in a formula, so we have the Fourier transform over g Fourier transform over g of t. So this big G of j omega, and here we just use the known result because it's a delta function and known is Fourier transform to 1. Okay. And then we just plug in this formula here, and okay, so this x of tau is actually g of tau here. Okay, so then it's 1 over j omega, big X of j omega should be 1 over j omega, g of j omega, and the big X should be big of g. So our x, so our Fourier transform of our unit step function x of t is g of j omega over j omega plus pi over g0 delta of omega, and then we just need to plug in our g of j omega. So g over j omega equal to 1, so it should equal to 1, and g of 0 is well, it's still 1. Okay. And so what do we get? It's 1 everywhere. So our big X of j omega is just 1 over j omega plus pi delta of omega. So this is a really weird function, but we believe it's true. So if you think a little more about it, you see it diverge everywhere because you have 1 over omega. So it really have a lot of singularity at omega equal to 0. You have this 1 over omega singularity, and you also have delta of omega singularity. But anyway, this is what people think the Fourier transform of unit step function is. It's very singular, and they look like this. Okay, and okay, so this is really singular, but we can make a little sense of it by applying the differentiation formula back to by applying the differentiation formula property back. Okay. So now we try to use the differential property back to get from big S of omega go to big G of j omega, and what we do is we multiply j omega on this whole thing. So j omega on this whole thing, then we have j omega, then this j omega and 1 over j omega cancel, it give you 1, and then the weird thing is the second term. So if j omega times delta of, so basically you have j omega times pi delta of omega. So that's basically omega times delta of omega. But by the, I think this is called sampling property. So sampling property of delta omega says that this thing times omega is just omega is 0. So that's just 0. Okay. Okay. So j omega times delta omega equals 0. So when you use differential property to transform it back, it just go back to 1. So as case, let's also draw this picture here. So we have so what we have here is so what here we have is g of t and go to big G of j omega, and then we have g getting integral, then it becomes x of t, and this is big X of j omega, and here you use this weird formula with delta of omega with delta function thing. Okay, let's try to say delta function, delta of omega plus. Okay, and yeah, so this is what happened, and so you can use the integration formula to go from g to x, and then we can check back by using the differential formula to go from big X to big G. Okay, everyone understand this idea? Okay, yeah, this is really singular, so we don't go into the detail of complex analysis, and but we just believe this formula is true. Okay, if we believe this is true, then we can go to more example. Okay, so more example, we now have a really weird thing. Okay, and okay, so what we do is this weird function. Now we have x of t equal to this weird, I don't know, slope function. Okay, x of t equal to this slope from -1 to 1. I guess we didn't. Yeah. So you have the slope 1, and so it's a 0 when so it's a 0 when it's all negative, and at -1 it suddenly jump to -1, and then go with the slope to +1 and jump to 0 when t is bigger than 0, t bigger than 1. Okay, and so we will try to use the differentiation and integration part. Actually, we don't. Yeah, so we try to use differential property to solve this. Okay. So what we do is we say we differentiation this, and so we have some g of t equal to dx dt. So we do d dt get g of t, and then we do Fourier transform. Supposedly you do differentiation, then you get easier g of t, and you get Fourier transform g of t. G of j omega, and then you try to write x of t as the integration. So you say x of t is the integration of so let's say x of t is the integration minus infinity to t, integration of g of t, then you use the integration formula to get big S from big G. Okay, so this is what we do. Yeah. Okay, and I guess one thing to say, so this is different from what we do in. Yeah, this is different from what we do in chapter 3, because chapter 3 we say we just do differentiation formula. And for the constant term, you just calculate it yourself. So I guess this is also a bit similar to the calculate constant term, calculate the A0 term, but here you better use this formula because it's hard to remember this pi delta function thing. Okay, so in this chapter we need to use the integration formula to change back from g to x. Okay, and anyway. So we have our x of t, then we do differentiation, then we find out that the differentiation actually have kind of 3 parts. Okay? So in the middle slope part, so obviously you do differentiation, you have this super 1, and you will get this 1 function here. Okay? But tricky part is you need to remember, you also have 2 delta function here to jump from 0 to 1, and you do differentiation, that's the delta function with -1. And then you jump from 1 to 0 is also delta function from 1 to -1. Okay. So this is our differentiation of x of t. So this is g of t. And then we do Fourier transform on this. And this is the sum of 3 functions that we already seen. So we can just write down its Fourier transform. So for the square wave, once again, square wave is should Fourier transform to this sinc function. And here just copy paste all the result for us to see. So it's 2 times sine omega t1 over omega, and t1 is 1. So this is 2 sine omega over omega. And then we have this 2 -1 times 2 Fourier transform delta function. So delta function Fourier transform to e to the j omega t. And so you have e to the j omega 1 and e to e j omega minus 1. So this is a Fourier transform of our small g, so this is big G. Okay, and then we use our formula. Okay, and we integration back g of j omega back to, we integration g of t back to x of t, and we need to check a little careful. So you integrate from negative infinity to t, actually x of t, and so negative infinity g of t is all 0, and x of t say all 0. Then you jump to the -1 and go to -1, and yeah, you should check out. Okay, And yeah, so xot indeed is the integration of GOT from negative infinity to t. And so big S of j omega is, you can plug in a formula, g of j omega divided by j omega times pi g of 0 delta of omega. And g of 0, there are two ways to calculate this. Okay, so g of 0 you can calculate just from here, and you plug in 0, and you kind of need to know the sinc function at 0 equal to 1. Okay, so sine omega over omega and omega equals 0 equal to 1. So this is 2 here, and then omega equals 0, this is 1 and 1. So 2 minus 1 minus 1 is 0. Okay, and another way to check g of 0 is that g of 0 is the integration of minus infinity to infinity g of t dt, and xot is the integration of g of t. So this is x over infinity minus x minus infinity. So x infinity is 0 minus x minus infinity is also 0. So g of 0 is 0. Okay. Wait, is this correct? And then confusing myself. Anyway, so g of 0 is 0 in this example, and yeah, so then we plug in everything, then we see x of j omega, so we don't have the delta function term. So x of j omega is just this thing divided by j omega, so you have this sine omega divided by j omega squared, and then these two things you can combine to cosine omega, and then divide by j omega. Okay, and then we can do a little checking here. So this thing is purely imaginary and art, because it's purely imaginary because both of them are divided by j, and this is sine omega divided by omega squared. So omega squared is even, and sine omega is odd. So this is odd thing, and cosine omega is even divided by odd function. So this is also odd. Okay. So this is purely imaginary and odd. And that check out with xot being real function, because we only plot on real plane, and on real line, and so this is real and odd. Okay, so this check out. You have a real and odd function, and its Fourier transform is purely imaginary and odd. Okay, everyone okay with this example? So yeah, so this is a little different from chapter 3. But basically, you plug in this big integration formula, and you plug in this integration formula, then you can do this integration thing for our Fourier transform. Okay. Okay, so this is a little confusing. Okay, so this is wrong because it was copying from previous thing. Okay, so let's close this out, I guess. So don't look at that. Sorry. And then let's go to the next topic. We have the time and the frequency scaling. Okay. And so what do I mean by time and frequency scaling? I guess we only have time scaling here, but we'll see frequency scaling soon. Okay. So by time scaling, we mean, we have x of t, and it transforms to big X of j omega, and then we think about x of at. So it's a scaling on time. Okay. So scaling on time, then we have Fourier transform x of at, and we can, derivation is not too hard, so you use this Fourier transform formula. So you do direct calculation, and you do a change of variable. So instead of at here, you say at equals on tau, and then what you do? So slightly tricky part is the substitution will depend on the sign of a, because if the sign of a is negative, you will actually change the upper and lower bound of your integration, because a is negative, then this positive infinity will become negative infinity, and negative infinity plus positive infinity. So you swap the upper and lower bound here, then you get extra negative sign. And so the end result you get here is, okay, so it is scaling with time, so you change at to tau. So the t is actually tau divided by a, so you have this divided by a here. Okay. And so you scale time by a, and you see that you scale omega by 1/a. So this is what we have expected all the time. So you stretch your time, then you squeeze your frequency, or you squeeze your time and then you stretch your frequency. But there is also this extra 1/a factor and with absolute value sign, because if a is negative, you have a negative sign here. So 1/a absolute value of a, and this omega divided by a. Yeah. And yeah, so this is our time scaling formula. You can memorize this and use it in various places. And the special case is a case that we already seen. That's when a equal to -1. So that's what happens when you do time reversal. Okay. So when you do time reversal, then x of t Fourier transform to big X or -j omega. So we already state this, and I guess here we just prove this once again. So you do time reversal on time reversal, then you also get a frequency reversal. Okay. And yeah, and this is time and frequency thing we say. Okay. And okay, so we have time scaling, and let's go to a slightly different topic. It means I think it should be okay, because although this is really long, but it doesn't really say too much. Okay, so do we have enough? Let's try. Okay, and the last topic we have here is duality. Okay, and this is also something we did have in chapter 3. Okay, so I guess we had a little bit. But now let's see this once again. So duality is saying that the time and frequency domain really has a really strong symmetry. So as an example here, we remember we have those two examples. So we have a square wave function on time, then we have the single function on frequency, and we have the single function on time, then we have square wave function on frequency. Okay, this is just the two examples we have, and the exact formula on this. Okay. But right now we don't need to look too much into that. Okay, just need to know they have this nice symmetry, nice transformation, and so on the shape they look like you have this strong symmetry. And the reason here is because these two equations looks really the same. Okay, you see this transformation from big X to small x and the transformation from small x to big X. They are basically the same equation, except that you have 1/2 pi here, and you have a minus sign here. Okay, right. So these two formulas are really similar. That's why when you change it from big X to small x and change it from small x to big X, you have a really similar transformation. So you can think about it, transform from this to this thing is very similar to the transform from this thing to this thing. And we can write this in a more formal way, is that if you have some small x function of t transform to big X function of x of big function of big X function of omega, and you can kind of I guess that's true here. You can kind of swap those two, right? So we put this big X function of j omega, and so you have the same function, but just say instead of a function of omega, it's a function of t. Then it will Fourier transform to the small x, so similar small x, but with in addition to swapping t to omega, you also put the extra minus sign on your omega and put the extra 2 pi here, and that will account for this extra 2 pi and the extra minus sign here. Okay? So easy way to memorize is, well, so you put big X here and you put small x here, but you put a minus sign on your omega to account for the extra minus sign, and the extra 2 pi here to account for extra 2 pi. And I guess we can do derivation really quickly. So we have our Fourier transform pair here. So our x of t is Fourier transform pair to big X of j omega. So we start from this equation, and we try to write, and then we try to turn this equation look like this equation. Okay? And so what we do is first we multiply 2 pi on both sides. So now you will try to change this thing to this thing. Okay. And so we multiply 2 pi on both sides, and the 2 pi now is on the left hand side. And then okay. So first we multiply 2 pi, and second we want to have a t and omega here instead of omega and t here. So we just swap t and omega on the second line. So t become omega, and omega become t, and omega t is still omega t. So d omega is dt. Now it's just change name. And the last thing is we change omega to minus omega, so you get a minus sign here. Okay, so 2 pi x over minus omega equal to this integration x over jt, and e to the minus j omega t dt. Okay, so now this equation. Okay, so now this equation look like this one. Okay, so we compare those two. Then we think that this 2 pi small x of minus omega is now the Fourier transformed function of this big X of jt. The big X of jt is now on this x over t slot, and the 2 pi x over minus omega is on this x over j omega slot. Okay, and okay, let's see one example of this really quickly. Is this thing. Okay, and so we have this function e to the, okay, so the function we just kind of calculate e to the minus the absolute value of t, and your Fourier transform to this 2 over 1 plus omega squared. Okay, and so this double-sided exponential decay go to this kind of rounded decay, rounded polynomial decay. Okay, and so then we put this function on the time domain, and then we'll see a similar function on the frequency domain. So what happens is put this function on time domain, you change omega to t, so 2 over 1 plus t squared, and then we see that it's Fourier transform of this function, so t changes to omega, and you multiply by extra 2 pi and get a minus sign on this omega. But you are in absolute value, so minus sign do nothing. Okay. And yeah, so this is what happened, and you can do various check to see that this is correct. Okay, and we have like 2 minutes, and 2 minutes we will finally go to we'll finish with duality, and in the 2 minutes. But anyway, I guess the bottom line is duality. You can do this kind of change and get a Fourier transform pair where the frequency function and the time function is swapped. Okay, and yeah. And we can also check that this is the same thing. This is not quite the same. Okay, so I guess this is the same if you swap this thing to the time domain, and then you swap this here. This is multiplied by 2 pi, and yeah, multiplied by 2 pi, and because it is an even function, so a negative sign on omega does nothing here. Okay, so this thing is this thing change t to omega, and multiplied by 2 pi. So this is also a thing. And we have 30 seconds, and I guess we should continue next time, but I will just show the result. So what we want to say is duality also works for some properties. And let's give a derivation, just see the result. So what we mean is that, so we have the differential on tan, and you get extra j omega on your big X. Then you can also have a differential on omega, you get extra minus jt. And you have a time shift, get extra e to the minus j omega t0. Then you can also have frequency shift, get extra e to the j omega t. And also you have this integration on time, get this weird thing, and you have a integration on omega. And I'm not sure why we don't say omega, but anyway, well, I guess that's a similar thing. Anyway, you have integration on omega here, then you get this minus 1 over jt, and also this delta function. And that's duality on yeah, this is a duality on the 3 properties. So differentiation, integration, and shift on time and frequency. Okay, so yeah, those are nice properties to remember, and I think I also summarized in a table in the later part of this slide. Okay, and the exact thing on time, no question, then we will stop here and continue on Friday. Okay. Thank you。
这个
你的作业。
这个它是。